All right, hello, welcome back. We're on section 7.3. Um, Sample means. What kind of data you have if you're going to generate a mean? What kind of answer you go up to somebody? What kind of thing are you getting from them? Are you asking them a question, yes or no, or are you taking some sort of measurement? Right? Means are for quantitative data, numbers. You can only take an average if you got some sort of measurement, right? So means are averages. So if we're dealing with sample means, we're talking about going up to some sample group and taking some measurement from all of them, and then average them and saying, oh, maybe this represents the average of the population that we sampled from. Remember that there's a big population. It has some true mean mu, and from it, we're going to take a sample. And from that sample, it's going to have some mean X bar. And we're going to use that mean X bar to make estimates about mu, to make guesses, inferences about where mu probably is, maybe tend to be, right? So sampling distribution of X bar. There are, once again, I'm going to keep saying it, there's a lot of vocabulary in this unit. Sampling distribution of X bar. Um, what does that even mean? That means if we repeatedly took samples and we got a bunch of averages from those samples, what would the distribution of those sample averages? Remember, what we're talking here is the distribution of all sample means from some population of size n. You take size n samples over and over, talk to 100 people, whatever, all the possible samples of 100 people. You get all the means from all those possible 100 samples. You plot them, that's the sampling distribution of X bar. So some things that are on your formula sheet. The mean of the sample means is the true mean. Once again, that means it's an unbiased estimator. Maybe one day you'll take calculus-based statistics and prove why that's an unbiased estimator. What a fun time. So I'll write above that unbiased. Standard deviation, sigma of X bar equals sigma of a radical n. I will remind you that for standard deviation, we need independence. To have independence here, we need to take less than 10% of the population. Remember, if we're sampling without replacement, we're kind of changing, it's like pulling cards out of a deck. Well, the deck's not the same anymore. So our odds change. If we're not replacing people, we need to take a sufficiently small number of people from that population or individuals such that we're not changing the distribution too much. Think of dealing cards out of a deck. Well, that's why card counters make money, because they know the odds have changed about what's going to come out. Anyway, so next, you want to, last time we established normality of p hat, and we said, okay, if we have at least 10 successes and failures, we can kind of wave our hands and see how that binomial distribution, people saying yes or no, things going right or left, that binomial distribution kind of converges to a normal distribution. You don't obviously see that here, so we've got a powerful theorem here, which we're going to kind of wave our hands about, the central limit theorem, and which says this: as the sample size gets large enough, what's large enough? I don't know. That's the wiggle. That's the hedging. As sample size gets large enough, as n gets bigger, more formally, you might write it as n tends toward infinity, right? It never gets to infinity, remember, but as n tends toward infinity, the sampling distribution becomes almost normal regardless of what the population looked like. So we could, regardless of what the distribution of the population looks like, whether it's this goofy parabolic distribution or this triangle distribution or a uniform distribution, or what appears maybe to be an exponential distribution where larger values decrease exponentially, exponential decay functions, those kind of things. Well, regardless of the shape of the initial population, well, if we take a small sample, think about that. We could take a small value and a small value, get that side over here. We could get a big value and a big value, get that side over here. Maybe get a small and a big and get something in the middle, right? But as we take more and more individuals, that's going to kind of average out, is what this central limit theorem says. It says that as sample size gets larger, as n increased, the distribution became more and more normal. We're going to say approximately normal. And look back to chapter 2, we need to be slapping that approximately word all over the place here. It's not perfectly normal. And we're lying to ourselves if we say this thing works perfectly every time. This is an approximation. It says it tends towards this thing. Does it always get there? No. So sometimes this breaks down. But as the sample size gets large enough, as n tends toward infinity, we can say these distributions of sample means, look at these are distributions of x bar. Notice these are distributions of sample means, where this top one was the population. Well, sampling from the population, we generate samples, get means from those samples. The plots of those sample means looks approximately normal under certain conditions. What are those conditions? For AP statistics, we're going to say that when n is large, that is n is greater than or equal to 30. So in here, we're going to talk about if n is at least 30, then we can go ahead with this approximation and say that x bar is approximately normal with a mean of mu and a standard deviation of sigma over radical n. And once again, we see that kind of relationship with the spread of x bar, that inverse square root relationship once again. I'm just going to make a little note of that. Let's highlight that square root n and remind ourselves, pull out purple, say this inverse square root with the sample size. Remember, as sample size goes up, the spread of your possible x bars decreases with the square root of n. So if we can make it 9 times bigger, we saw yesterday, the spread is going to be 1/3 of it. What else could I do to show the data is approximately normal if I don't get to that n is equal to 30 threshold? I could look at a histogram. I could look at a dot plot. Look at some sort of, probably a histogram or box plot to assess maybe skew or symmetry. Right. And so once again, we have to assess normality. For this thing to hold, we're going to eventually need to find probabilities, right? We want to know where do sample means fall, right? Because the sample mean doesn't always hit the target. But, if I know how big the sample was, I can say it was probably a certain distance from the target. I don't know if I missed high or low, but I can say, okay, it's probably within such a range. And those kind of statements saying it's probably within such a range, that's what's going to allow me to create confidence intervals in the next chapter. When do I use the 10% rule? I use the 10% rule to establish independence. There's going to be an independence condition we need to check. Independence to calculate the standard deviation of x bar. Remember up here, this is the mean of x bar, and this is the standard deviation of x bar. The mean of the sampling distribution of the sample mean, and the standard deviation of the sampling distribution of the sample mean. That's a lot of vocabulary, right? Please, I'm going to keep saying it. Go back, make some note cards. So you need independence to calculate the standard deviation of x bar. Otherwise, some assumptions break down, namely that the probability of success, probabilities are no longer fixed. True or false? If the population distribution is approximately normal, and the sampling distribution of x bar, no matter the sample size, is also approximately normal. That's true. Always true. If x is distributed normally with mean mu standard deviation sigma, then x bar is distributed normally mean mu standard deviation sigma over radical n. That is regardless of n. So if the population's already normally distributed, then you can think about, well, what is the mean then if the population's already normally distributed? The mean is a combination and a transformation of an already normal distribution. And thinking back, oh, look at that. Chapter 6 kind of stuff, which we'll probably quiz about soon. If you're watching this in the spring, I'm sorry. So we'll see that soon enough. And if you see me in person one day, I'll show that derivation, how we can get to x bar from x using those formulas from chapter 6 section 2. So I'm going to skip this little example down below and move on to the next page. At the Peanutty Peanut Company, great. What an awesome example. Dry roasted shelled peanuts are placed in jars by a machine. Okay, don't do it by hand. Distribution of weights of the jars. All right, so weight of jar, let's call that X. And X is distributed approximately normally with a mean of 16.1, standard deviation of 0.15. So that's the population. That's saying the average jar has that mean and standard deviation. All right. A, without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding its contents weigh less than 16 ounces. Okay, so that's the probability that X is less than 16. Or randomly selecting 10 jars, single jar, less than 16, 10 jars, average, less than 16. Well, which is more likely? Probability X is less than 16 or probability X bar is less than 16, given that N is 10. All right, well, which one is more likely? The more likely, think about it this way. When are you, 16 is a result, some distance from the mean. It's might be extreme value. When are you more likely to get extreme values? Consider that. Do you get extreme values in individual results, or do you get extremes when you start to average a bunch of things? Well, you're more likely to get an extreme result if it's an individual observation. And how does that make sense? Take a look back here. As you take larger samples, the spread of your expected values goes down. So if your sample size is 1, you're not dividing by anything. But if your sample size gets larger than that, again, inversely proportional to the square root of the sample size. Kind of the intuitive explanation is extreme results are more likely with smaller sample sizes. Individuals all over the place. Averages of large collections of individuals tend to be pretty close to the truth. Wisdom of the crowd. Part B says find the probability of each event described above. Well, on the left, it's easy. The probability that X is greater than 16, we already know how X is distributed. X is distributed normally with a mean of 16.1, standard deviation of 0.15. So you can say, oh, well, I know how to find those probabilities. 16.1, call 16 right there. We're finding that left area. How do you find that? Norm CDF. Knock it out. Norm CDF, lower bound, upper bound, mean, standard deviation, negative infinity up to 16. Mean is 16.1, standard deviation 0.15. And I'll label those low, up, mu, and sigma. I'll look at the key in a moment to find those values. Need to be able to do that. On the right side, if we're going to find a probability involving X bar being greater than 16, we need to establish the distribution of X bar, and we haven't yet. But luckily, we were told that jars is approximately normal. And so if jars is approximately normal, then we can also say that X bar is approximately normal. Mean is still going to be 16.1, but the standard deviation now is going to be 0.15 divided by radical 10. That is there. What is that? That's sigma of X bar equals sigma over radical n. Again, going to keep saying it. The spread of your sample statistics decreases with the square root of the sample size. You take bigger samples, your spread of your expected values goes down. It's like I keep saying it because it's an important concept. If you wanted to find that, you got to put that in your calculator. I'll find the one on the right with you. First thing I might notice is, okay, well, radical 10, that's a little bigger than radical 9, and radical 9 is 3. So I can think of my spread going down by a factor of 3. A little more than that. 0.15 divided by radical 10, put that in, and that's 0.047. All right. 0.0474. So I could draw a picture once again. But now, if I put 16.1 here, my spread is 0.0474. So 16, well, that would mean this one standard deviation is like 16.05, 16 would be all the way down here. It's almost 2 standard deviations away now. Well, if it's 2 standard deviations away, I can kind of use empirical rules, say, what, 68, 95 is within 2 standard deviations. So that means 5 is outside. And since it's a symmetrical distribution, half of 5 means 2.5 is probably going to be down there. So my rough estimate's about 2.5%. It's probably going to be a little less than that. So let's do this one. I'll do the one on the right with you. Norm CDF, lower bound, upper bound, mean standard deviation. Everything's the same, 16, 16.1, but except for our standard deviation is 0.047. And I'll label those low, up, mu, and sigma. If you're not labeling these every time, why? Start labeling them. If you're not making statements like this every time, you don't understand it. All of this is the problem, not the answer. This is not the answer to the problem. All this is the answer to the problem. You put that in your calculator. Let's do that. Second vars, norm CDF, lower bound, upper bound, mean, 0.047 standard deviation. And we get a value. Look at that. My empirical rule still works. 0.017. Let's call it 0.0167. A little bit less than the 2.5% that the empirical rule kind of suggested as an upper bound of the values. Doesn't really have an expectation for the lower, I mean, more than 0.015, but we knew that. So, okay. So that is an example of what a calculation might look like involving X bar. Expect one of those. Expect that in a multiple choice kind of setting. This next one, I'm just going to tell you, just go ahead and write like test FRQ by it. This you're going to see this. I love this FRQ. You're going to see this. Promise. So think about this one. You look at this problem and you're not going to know why it's in this unit right away. Suppose the total number of snaps sent during a typical day by a randomly selected high school student follows a right skewed distribution. Okay, so we're interested here today in the number of snaps sent. And it follows a right skewed distribution. So the population isn't normal, all right, with a mean of 15 and a standard deviation of 35. All right, assuming that students at your school are typical Snapchatters, okay, assumptions, how likely is it that a random sample of 50 students will have a total of more than 1,000 snaps in the last 24 hours? Total. So I'm asked to find the probability that the total is greater than 1,000, but I don't know what the total has to do with the average. Well, do you know? How can you get from the total to the average? Let's think about how we might write the total. The total comes from adding them up. The sum of the x's is greater than 1,000. Well, what relationship does the sum of the values have to the average? How can you get from the sum of the values to the average? Well, you can do that by dividing by n. If we divided both sides by n, the sample size, in this case, which happens to be 50, then we're now saying, instead of trying to find the probability the total is greater than 1,000, we can turn this into a probability that the average is greater. 1,000 divided by 50 is 20. So I'm going to write this at the top. Please, dear God, understand this is coming on the test. Turn questions about totals into questions about means by dividing by n. Turn questions about totals into questions about means by dividing by n. But what does that mean? Guys, the sample mean is the total divided by n. So if we have a question about the total, which is the numerator of this, we can turn it into a question about x bar if we divide both sides by n. And once we've done that, we can say something about how x bar is distributed under certain conditions, which we've outlined here. We're going to keep coming back to that. So we need to first establish how, X bar is distributed. So I'll restate this. Finding the probability that the total of the x's is greater than 1,000. That's the same as finding the probability that the average of the x's is greater than 20. Once again, that came by dividing each side by 50. That is the sample size. All right, so now we have to establish, well, if I want to find a probability about that thing, I better establish how that thing is distributed. So X bar, let's say X bar, well, we talked to 50 students. Since n is 50, X bar is just going to be distributed approximately normally. We have that. We have this normality because the sample size is at least 50. So X bar is distributed approximately normally. And I know that because of the central limit theorem. CLT says that if our sample size is at least 50, our X bar, our sample means are distributed approximately normally, regardless of the sample size, regardless of the population distribution. Mean is 15, that's mu. Standard deviation is 35 over radical 50. That is sigma over radical n. And that turns into 35 divided by radical 50, turns into 4.95. All right, so all of a sudden we've turned a question about a total, which we didn't really know how to deal with, into a question about the mean, which we do know how to deal with. That's good. So now we can find the probability that X bar is greater than 20. We know the mean, we know the standard deviation. Draw a little picture for yourself. If you aren't drawing pictures, why? Start drawing pictures for me. 15 greater than 20, 4.95 would be about one standard deviation above. So I'm going to put 20 right about here. I'm going to shade that left area. How do we find that? Probably going to find it with a norm CDF. Lower bound of 20, upper bound of positive infinity. You're going to type it in as a bunch of nines. Mean is 15, standard deviation is 4.95. We'll label those low, up, mu, and sigma. And we're going to find that probability. It's more than one standard deviation above. I expect this probability to be a little less than, well, 68 is within one. That means 32 is outside. Half of 32 is 16. I expect my answer to be a little less than 16%. Let's make sure. Norm CDF, what are we doing? 20, bunch of nines, mean 4.95 standard deviation, and we get an answer, hot dang, 15.6%, 0.1562. Cool. So there's about a 15% chance. Great. Big idea here. You need to be able to turn questions into totals, questions about means, by dividing by n. You're going to have a question in your homework. It's going to be a question about airplanes. Make sure you can do the airplane problem. So I'm going to write out the side, homework, airplanes. Look back at this problem when you come to that homework problem about airplanes that you don't understand. Pause. I've been talking a lot. You guys need a chance to try this one. We've seen this question before. We've seen part A and B to this before, talking about stopping distances of cars. You guys try 2009 number 2 by yourself. Give us a shot. What's the probability that a randomly selected sample of 5 cars will have a mean stopping distance of at least 130 feet? Excuse me. You need to establish the distribution of the sample means. You need to find the probability then that sample mean is greater than 130. Take a moment to try that. All right, we'll look at this one, solving using z-scores. Mean stopping distance of at least 130 feet. Well, are you missing? No, you weren't missing something here. The mean is 125. Standard deviation of the population was 6.5. But since we have a sample of size 5 divided by radical 5, so that makes the standard deviation 2.91. Finding that probability, X bar greater than 130. That's the same as finding a z-score. 130 minus the mean, 125 divided by standard deviation, which has a division in it as well. And you get a z-score 1.72. Using your z table, you get 0.0472. You could use norm CDF here, would have been just fine. I think you get an answer that's off by a decimal or two, thousandth, maybe a 10,000th. So, all right, I'm gonna skip one of the middle examples to keep this lecture digestible, and we're gonna do one last example here: the length of human pregnancies. We've talked about this one already a little bit, I think. Gestational period for human pregnancies, approximately normal with a mean 266, standard deviation 16 days. Great. So we could say if X is pregnancies, human pregnancy, and then X is distributed normally with a mean of 266, standard deviation 16. Great. If you're not defining your variable, both in words and in terms of its distribution every time, you are missing out on a chance for easy points, and it really shows me that you understand the problem and you need it. So just do that. State your variables, say what it is, and say how it's distributed. Find the probability that a randomly chosen pregnant woman has a pregnancy lasts for more than 270 days. One woman. So what's the probability that X is greater than 270? Well, that one's pretty easy with a norm CDF. Norm CDF, lower bound, upper bound, mean, standard deviation. I can see that that's about a quarter of a standard deviation. It's going to be most of them, a large proportion. You do that with your norm CDF function. Second bars, norm CDF, lower bound 270, upper bound bunch of 9s, 266, 16. And we get an answer 40%. All right, so 40% of pregnancies, 0.4013, last more than 270 days. Cool. Suppose we choose a simple random sample now of 6 pregnant women. Okay, let X bar be the mean pregnancy length of that sample. What's the mean of the sampling distribution of X bar? Well, the mean of X bar is the true mean mu, which is 266. Even if we take 6 people, we expect the average of those 6 people on average will be the truth as well. Remember, it's an unbiased estimator. What's the standard deviation of that sample mean going to be? It's going to be smaller than the spread of an individual. Sigma over radical n, that's going to be 16 over radical 6. That is, whoops, not 16 times radical 6, 16 divided by radical 6 is 6.53. So the spread of the average of a collection of people is smaller than the spread of an individual. Not surprising. So we've computed that standard deviation. Find the probability that the mean pregnancy length exceeds 270. So now we're going to find probability that X bar greater than 270. You should be able to do this. We've established the mean. We've established the standard deviation. Do we know if it's going to be normal? We do. How do we know that X bar is going to be approximately normal? We know it because the population was normal. X bar was approximately normal. I'm going to write this in green since X is distributed approximately normal. Since we have that, we can say that X bar also will be approximately normal. With mean of 266, standard deviation of 6.53. So we should expect fewer above 270 in this case. We do that, we're going to do it norm CDF. Only difference between this one and the one above is that instead of 16, we're going to have 6.53. Remember, go back and label these lower, upper, mean, and standard deviation. I forgot to up here, lower, upper, mean, and standard deviation. When you do that, second bars, distribution, normal CDF, 6.53, 27%. So, less common. Yeah, so mu X bar and mu of X bar, make sure you know what these are. Mu is the mean of the population. X bar is the mean of the sample. And mu of X is the, mu of X bar is the mean of the sample means. So, make sure we know those differences. There's a lot of vocabulary here. So we've got more examples beyond this. We've got a number of FRQ examples. just as we have Chapter 6 FRQs, which I've kind of left in the bag, we're going to have some Chapter 7 FRQs. We'll approach those in the days leading up to the exam, that last week or the week before. I don't know. Whatever, how the schedule works out, we'll approach those before we test. So good luck, Godspeed, and we'll see you around.